From the wheels of your car that carry you down the road, to precision axes that keep 3D printers moving, modern machines are full of clever ways to turn rotation into straight line motion. But there's one such mechanism so strange it almost looks like a mechanical illusion. It has no threads, no gears, and no belts, and yet it creates perfectly smooth linear motion. This is the threadless ball screw, and in this video we'll discover where it came from, how it works, and an unusual quirk that might just explain why it never took off. But first, we need to go back to the mid-2000s at the birthplace of low-cost consumer 3D printers with the RepRap project. Started by Dr. Adrian Boyer, a senior lecturer in mechanical engineering at the University of Bath in England, the RepRap project aimed to create a low-cost, open-source machine capable of self-replication, and the team chose 3D printing as the core technology to achieve that goal. The RepRap project rapidly grew to a range of open-source designs you could build yourself with 3D printed parts printed on a friend's RepRap. But obviously you can't 3D print every single part, right? You still need the fasteners, electronics, motors, and you need a precise and reliable way of converting the rotation of those motors into linear motion for the X, Y, and Z axes. Unfortunately, precision linear motion components are expensive, and at the time, almost impossible to find. Without a low-cost solution, the RepRap project was dead in the water, so people began to experiment with different ways of creating linear motion on a budget. And let me tell you, they came up with all kinds of wacky solutions, but one of them has always stood out to me as the most ingenious: the threadless ball screw. But before we figure out what a threadless ball screw is, what the heck is a regular ball screw, and will this video now get demonetized? Well, a ball screw is a clever implementation of a linear actuator that solves most of the problems found by simply driving a nut up and down a thread. This will absolutely turn rotation into linear motion if you prevent the nut from rotating, like with this cheap threaded rod, but the losses are huge due to sliding friction. But ball screws mitigate this by introducing, well, balls, like in a ball bearing. Instead of two metal surfaces rubbing against one another, the balls roll along a specially machined track and are constrained in a cage that cleverly recirculates them as they do so. You can think of a ball screw as if someone got a regular ball bearing and somehow dragged it out into a helix. Ball screws are the gold standard of translating rotation into linear motion with high precision and efficiency, and are used extensively in industrial equipment and automation. But as you can probably imagine, they are a precision bit of kit and they cost a lot. So much so that even today, you're unlikely to see them used in consumer 3D printers unless it's in something fairly special. And 20 years ago, in a project aimed at making 3D printers more accessible, zero chance that ball screws would have been chosen. But believe it or not, this clever arrangement of ball bearings on a smooth shaft is remarkably close to the principles of ball screws. It still converts rotation into linear movement, but instead of a physical thread or machined feature guiding that motion, it all comes down to the angled bearings as they interact with the rotating smooth shaft. Here's how it works. The three bearings are arranged radially around the smooth shaft and preloaded to grip it tightly. If they are perfectly in line with a linear rod, well, then it would be no different to a regular ball bearing, and the mechanism would remain stationary as the shaft rotates. But look what happens if we tilt them ever so slightly. Now, when the shaft rotates, the bearings trace a helical path which climbs up or down the rod as it turns, creating smooth linear motion. Or to put it another way, an unthreaded shaft in association with a surrounding cluster of inclined rollers develops different forces associated with relative motion between the shaft and rollers. That word salad is from the introductory paragraph of the patent for linear actuators invented by Milton N. Weber and granted in 1964. Weber's patent is an interesting read, and he positions the invention as a novel kind of linear actuator, which he proposes could be used in textile loom shuttles or the actuation of garage door opening mechanisms. And you really do have to keep the filing date in mind, Mechanical automation was very common and well established in the industry by this stage, but any kind of electronic or computer-controlled automation was still a fair way off. In fact, G-code, the coded instructions used to control CNC machines and 3D printers, had only just been standardized in 1963. Instead, what was common were machines like auto lathes that used mechanical programming instead, with cam stacks to automate basic tasks. And unlike other approaches, he states that his design would be more cost-effective to produce, and that the need for screw threading is obviated. Now, that right there is an excellent word. I'm definitely stealing obviated for a future combat robot name. It means to do away with. And with the patent as a rough guide, I built this simple linear stage to begin my experimentation with threadless ball screws. It uses a 8mm linear rod driven by a NEMA 17 stepper motor, and I 3D printed the bearing assembly. It's secured to a linear rail, which forces it to translate instead of simply spinning, and it runs some super simple Arduino code using the Accel stepper library. I used some ball bearings I had on hand, and my first implementation was fairly rudimentary, but it still produced surprisingly smooth motion. Like the thread pitch on a screw, the tilt angle of the bearing determines the amount of linear movement per rotation of the shaft, and that can be precisely set at the design stage to achieve the desired outcome without any special hardware. This means that different reduction ratios can be quickly iterated on and tested using the same set of linear rod and ball bearings. In fact, there's nothing stopping you from having multiple assemblies on the same shaft but with different tilt angles, which means that they'll move by different amounts for the same rotational input. You could even have two carriages moving in opposite directions by mirroring them. Pretty neat. But how do you know how far the carriage will move per rotation of the shaft? Well, at first, I had no idea, so I asked someone way smarter than me, James from Broken Link Robotics, and it turns out that all you need is good old-fashioned trigonometry. This is the equation. It's just tan equals opposite over adjacent once you boil it down, but yeah, it did take me a little while to wrap my head around it. Theta is the bearing tilt angle, y is the circumference of the central linear rod, and x is the distance that will be travelled for each full rotation. You notice that the rod diameter matters, but the bearing diameter doesn't, which I thought was pretty interesting. So to figure out how far a carriage with a 20-degree bearing angle travels with one rotation of an 8mm diameter shaft, you need to do the following. Tan 20 equals opposite over adjacent, with adjacent being the circumference of the rod, so in my case, that's 8 times pi. You do a little arranging and you get tan 20 times 8 times pi, and that gives us 9.148 millimeters of travel per full rotation of the shaft. A big thanks to James for reawakening those repressed memories. So, a 20-degree bearing angle equals 9.148 millimeters of linear movement per rotation. And this stepper motor has 200 steps per revolution. That gives us 21.863 steps per millimeter times whatever microstepping amount that you're running. I put together a basic Excel spreadsheet to help me figure this all out, and the relationship between bearing tilt angle and millimeter travel per rotation did seem nice and linear, at least at first, but then I decided to graph it. Indeed, it is a very straight line as you gradually increase the bearing tilt, but then it starts to accelerate exponentially until it explodes off into space. I did not expect this at all, but then it clicked. If a bearing is at 90 degrees, then that's no longer a tilt, they're just perpendicular. And obviously that means that it's not going to function at all, but as you approach that 90 degrees, the numbers get more and more ridiculous. I think it's really funny that you can have a theoretical bearing carrier with an 89-degree bearing tilt, which would move almost 1.5 meters per single rotation of the shaft. Now, you wouldn't even be able to drive that in reality, but what if we instead go in the opposite direction? Can you tilt the bearings by an almost imperceivable amount to achieve a crazy high reduction that basically starts to approach infinity? Well, maybe, but even at a 5-degree angle tilt, it was becoming clear that FDM 3D printing wasn't going to cut it. It just wasn't accurate enough. So I got these custom blocks made using this video's sponsor, Justway. With Justway, you can get your parts made with a huge range of industrial processes, from CNC machining to sheet metal fabrication, injection molding, and of course 3D printing. I designed these high reduction bearing carriers with various bearing angles to test out. This one is 5 degrees, this one is 1 degree, and this one is a ridiculous 0.5 degree tilt. It was all very easy. I simply exported them as a step file from Fusion, then I uploaded them to Justway's quoting engine. From there, you can choose from a load of different printing processes and materials. I went with UTR 8360, which is an affordable but high precision UV resin using the SLA printing process. And for parts of this size, the SLA process has a tolerance of plus or minus 0.2 millimeters, which is well beyond what you can achieve with filament-based 3D printing. The parts came out really clean, and I'm glad I remembered to mark the bearing tilt on each one because you can barely even tell these two apart. So let's see how slow we can get this carriage moving. The 5 degree carriage is already very slow, moving at a sluggish 2.2 millimeters per rotation, but moving to the 1 degree carriage is absolutely ridiculous. The shaft is spinning super fast, but it looks like it's barely moving the carriage at all, and at just 0.44 millimeters per revolution, it is indeed barely moving. But the 0.5 degree carriage takes the cake. Yep, look at it go. At 0.22 millimeters per revolution, this thing is just silly. But if you wanted to make something move at a glacial pace in a single reduction, this is pretty much the only way I could think of how you'd be able to do it. You too can use Justway's services to create all kinds of things, and you can get $10 off any order of $30 or more with a coupon code JustWay-MakersMuse10. You can learn more in the video description below, and a big thanks to Justway for sponsoring this video. And now it's time to address the elephant in the room. How accurate is it? Honestly, I had no idea what to expect. The math works, but this mechanism is unlike any other approach I know of. There's no physical threads or teeth like you'd find on a gear or timing belt. It relies on friction alone to lock the rotation of the shaft and bearings together. There has to be a reason this never took off, so it's time for yet more testing. To find out, I've put this Jeep together. So I've figured out the correct steps per millimeter for a 5 degree bearing tilt, which is set up here on this slightly updated version of the threadless ball screw. And I've got this little marker going along the ruler. And all this is going to do is run back and forth 100 millimeters, or at least that's what it thinks it's going to do. And then pause so we can see what the reading is. So the thing about the threadless ball screw is you can just move it. So I'm going to move it to the 10 centimeter mark here. So we're starting off on a good point. And we're going to let this run for 1 hour. So I've got a stopwatch here. I'm going to plug it in and we'll get started. Well, that went south very quickly. Literally. I had intended to run the setup for an hour, but instead of just drifting somewhat randomly like I assumed it would, this simple version of the threadless ball screw appears to bias to one side, which is annoying for precision. That's a pretty interesting behavior, and I wondered if the plastic was flexing ever so slightly while the carriage is in motion, which changes how the bearings grip the shaft, or maybe it even alters their tilt slightly. It is just PLA after all. To make sure it wasn't my dodgy code influencing the results, I tried flipping the carriage and running the test again. And yep, this time it just migrated in the other direction. During my research, all of those early RepRap experiments in using threadless ball screws were similar to my design. 3 bearings supported on one side with a simple 3D printed carrier. If this is the kind of behavior that those people were experiencing way back then when they tried to use this as a replacement for ball screws, no wonder it didn't work out. But then I began to wonder, if there's a bias to one side, maybe we can just balance it out. How about something like this, with 6 bearings instead? 3 on each side, and rotated to ensure they all share the same tilt angle. Now that's more like it. This version was much more stable, but over time you can definitely see it still favors one side. Slightly. It did take almost 30 minutes, but eventually the carriage drifted into the side of the shaft coupler and began to slip. It might be possible that the slightest variations in geometry or tension is affecting repeatability, and with a bit of tweaking you may be able to improve it. But maybe in your application, you don't need absolute precision. You just need to move something. So the next obvious question is, how much force can a threadless ball screw exert before it just, well, slips completely? Now, this is where things got really interesting. For this setup, I've got the guts of a kitchen scale attached to the bearing carrier with a small chain, and I've adjusted the code yet again to run the motor continuously forward for 100mm before moving back only 20mm and then trying again. Unlike my earlier tests, this threadless ball screw can be tensioned by tightening the long M4 bolts on each side. This increases how much force is imparted by the bearings onto the smooth shaft, and it lets us do some pretty cool things. To start, I ran the carriage with no tension at all on the bearings. Only the 3D printed assembly is holding them in place, and as such, it just slips with a pulling force of barely 70 grams. That's really not much at all, so I started to slowly tighten the bolts by only a quarter of a turn each time. With just 1/4 turn, the pull force jumped up to around 680 grams. That's almost 10 times as much as with no tension and already approaching usable territory for a linear stage. Another quarter turn jumped it up again to 1,800 grams, and the motor is showing zero signs of struggling. In fact, the pull force is remarkably stable, although the relationship between the bolt tension and pulling force is clearly not even remotely linear. And this was made all too evident when just one more quarter turn resulted in the scales throwing an error. It turns out the guts of this kitchen scale only has a max weight of 3 kilos before it errors out. And yes, that spring coupler will be influencing results quite a bit, but I honestly didn't think this mechanism was capable of anywhere near that level of force. That may have been a bit naive of me, because you can see just how much the setup flexes by turning it by hand. And I need to note that both sides were screwed down into the plywood for this test. But then I got to wondering, could the tension be fine-tuned to such a degree that I can approach the maximum this scale can measure without going over? I had to go with the current setup, adjusting each side by a tiny amount each cycle, and admittedly it did take quite a bit of trial and error, but eventually I got it to behave like this. And you've got to admit, that level of repeatability is pretty remarkable. I managed to manually tune the tension to 3 kilograms with a tolerance of, what, plus or minus 10 grams? I let it run for a while and it stayed within that range with no issues at all. And I think it's just so satisfying to watch in action. By the way, if you like satisfying mechanical projects like this, then you should definitely consider subscribing because I'm bringing them back to the channel. So, the scale is maxed out, but this setup is clearly capable of way more force. So I added a bearing and spacer to prevent the shaft coupler from crashing into the bolt heads, and I cranked the tension bolts down super hard until I found the limit of the stepper motor. What a lovely sound. From here, it was just a matter of backing off tension bit by bit until I found the maximum force output the system was capable of safely delivering. And have you noticed how quiet this thing is? The stepper motor is by far the loudest part, running at half microsteps, but when the threadless ball screw slips, it does so with a smooth rubbing sound. No doubt there's wear going on, but it seems pretty minor, and you can always just readjust the tension as the system wears in. And at this tension setting, the carriage has no problem pushing the entire 10mm thick plywood board back and forth on top of the table as I try to wrestle it still. Yet, when it does collide with something the motor can't overcome, it slips, safely and reliably. Now that is impressive. And that must have been what Milton N. Weber thought of his invention, because he details a fantastic use case in the hinged tailgate of an automobile. Because, if you haven't guessed it yet, that right there, that's the rear of a vehicle. He states that automatically powered closure mechanisms present a real and serious risk of grave accidental bodily injury if limbs are not removed from the path of closure. But when using the improved actuator mechanism, the window can slip or stall while exerting thrusts towards closure, which are not so great as to inflict serious injury upon any occupant who may become accidentally trapped by it. Now, it has been over 60 years since this patent was granted, and automation control circuitry has come a long way, but I can think of a few modern car companies that could really benefit from this invention. Unfortunately, this unique advantage of threadless ball screws is exactly the reason that they never took off for 3D printers. It's simply not precise enough. Over time, even the most precisely engineered solution will drift due to flexing or bearing and shaft tolerances, or wear, or lubricants, or all of the above. And for applications like a 3D printer that require absolute precision and linear movements are done hundreds to thousands of times in a single print, that'll ruin your day super fast. And at the end of the day, the threadless ball screw and many other innovative approaches lost out to this, the humble Acme threaded rod. Acme lead screws have a trapezoidal thread form, which is squared off slightly compared to the triangular shaped thread form used in regular bolts, and they are a strong and repeatable solution for linear motion applications where a built-in reduction is required. They're not perfect by any means, there's still quite a lot of sliding friction between the bronze nut and the thread itself, and they have significant backlash issues compared to a ball screw, but for the z-axis of a 3D printer, gravity deals with the backlash, and lube helps keep things moving smoothly. The Acme thread standard was developed in 1894 by the Acme Screw Machine Company. Yes, a real company called Acme, so they're not exactly new, and the modern metric version is a trapezoidal thread form, but way back at the beginning of the desktop 3D printing revolution, either trapezoidal threads or Acme screw threads were really hard to find outside of industrial applications. But fast forward today, thanks to the explosion of interest in budget 3D printers, you can now easily buy Acme lead screws and nuts in a wide variety of sizes and pitches, and pretty much every 3D printer brand on the market now uses them. So that's 3D printers out, but don't count out the threadless ball screw, because I can see this thing being useful for so many other applications today. Maybe you're designing an automation system that has to move a carriage from point A to point B, but you don't want to worry about sensors, programming, or end stops, then this will do it, and it just slips a little bit at either end. Or maybe you're into kinetic sculpture and want to move things around, but don't want to create a dangerous pinch point hazard for curious fingers. You can tune your tension to be super light, and you're good to go. When curious fingers get stuck, it'll just slip, and there's no lawsuit. But in my case, I am busting to see if I can use a threadless ball screw in a combat robot to actuate a lifter. Gears and motors don't like being backdriven from sudden large impacts, so it's hard to make a lifter durable enough to survive against the modern nasty spinning weapons in today's combat robots. But if an actuator itself could slip a little instead, it might be powerful enough to do the job, but protect the gear motor and linkages when they inevitably get uppercut by a chunk of steel spinning at 8,000 RPM. This is what I've got so far, so watch this space. And if you want to learn more about fascinating mechanisms and 3D printing technology, then you're in the right place, because here on Maker's Muse, it's my aim to empower your creativity through technology. A big thanks to Justway for sponsoring this video. You can find a link to download my final version of the threadless ball screw in the description below if you'd like to play with it yourself. Thanks for watching, guys. Bye.